Hello and welcome everyone. Thank you for joining us today. This webinar is hosted by Tecta and the topic today is moisture risk in modern construction methods. Modern construction is evolving rapidly. We're seeing greater use of timber and biogenic materials, more advanced prefabrication methods and increasingly complex building systems. But that's especially in areas such as roof structures and building envelopes. So while these developments bring major sustainability and efficiency benefits, they also introduce new challenges. One of the most critical is moisture risk. Moisture has always been a concern in construction, but as building systems become more complex and materials become more sensitive, the consequences of poor moisture management become greater, from hidden moisture accumulation in timber structures to vulnerable roof assemblies and building interfaces. Even small oversights can lead to costly rework delays, compliance issues, and long-term building performance problems. So in today's webinar, we're going to explore how moisture risk is evolving alongside our modern construction methods. We're going to look at how different materials influence moisture behaviour, how they identify the parts of a building that are most vulnerable, and discuss why targeted protection is becoming essential for successful projects. We'll also move beyond theory. So during this session, you're going to see how moisture management can become traceable and actionable in practice. Through a live project demonstration, we're going to show how Tecta tracks moisture conditions in real time and turning environmental data into clear insights that support decision-making, improve the accountability, and help prevent costly mistakes before they occur. So by the end of the session, you'll have a clearer understanding of how timber, biogenic materials, and complex construction systems influence moisture risk, which areas of the building require the most attention and protection, how real-time monitoring translates moisture data into actionable insights, how traceable monitoring improves accountability, prevents disputes, and supports compliance. And we'll give you practical approaches that you can apply immediately to protect your projects from moisture-related risks. So whether you're involved in design, construction, quality assurance, or project management, this session should give you a good practical hands-on look at moisture management in modern buildings. There'll be three parts to the webinar. I'll be presenting on the introduction, the background to materials, and a little bit on the moisture risk side of things in construction. And then my colleague Tice will be giving a demo on intelligent monitoring and tracing moisture issues from real projects. So just to add a note there, we will be demonstrating the Tecta product at the end of this. And then at the end, we'll open up for a Q&A session. So please do add any questions in the comments section. Okay, let's begin. So, as I said, I just want to introduce a little bit into the background of the problem in moisture risk in construction today. And I'm just popping up a few headlines from media articles there on the screen, which you may or may not have heard of. The one in the sort of top middle is a situation where a lot of moisture, trapped construction phase moisture and continued water ingress into a mass timber roof construction resulted in huge claims, up to £4 million in damages of a rotten, decayed timber roof. And unfortunately, those claims weren't recoverable and ended up the main client in a more of a desperate attempt to try and claim through somewhere and even to try to take it to the architects, although they were unsuccessful on that case. A very large, high-profile claim is the Sky HQ in West London, and I think I'm not sure if that's been resolved yet or it's still in litigation or close to being resolved, but that claim is, I believe, into the hundreds of millions now as a result of water ingress into the cassettes in the roofing system and subsequent damages and repair costs that went with that. The insurance side of things aren't necessarily going to cover all of those damages, so someone has to be accountable for the damage costs, and that could end up being the main client or the contractor or whatever's decided in the courts. And last October, a new law, particularly in the UK, was introduced, Awaab's law, and that is relating to a requirement and some regulation behind in-service accommodation that requires a responsible amount of healthy living environment and air quality. And we're talking about things in terms of surface molds developing and causing hazardous to health. So there should be adequate ventilation and provision in place to ensure that doesn't happen. Now, all of these issues and many more as well in the headlines are result of water and moisture in buildings that can be prevented with the correct design and installation, correct systems, but also through monitoring and early prevention. Back in 2021, the government in the UK released the Net Zero strategy to build back greener. This is all about becoming net zero by 2050. And in that strategy, there is an encouragement and an incentivisation scheme of using more timber and other biogenic materials in construction. So they see that by achieving net zero, we need to use more biogenic materials to do that, which is a very good thing. By doing that, we're embedding the net zero into decision making in the construction industry, and that falls into society and governments. That comes through into the design stage, and as a result of that, the Timber and Construction Roadmap was released in 2025, which gives added introduction and guidance into how that can be achieved. Off the back of that, globally, there are many certification and accreditation schemes that allow that you can sign up to and your project can be part of, and you can showcase that you are doing your bit towards providing that net zero target that's been encouraged. And some of those schemes are just presented there at the bottom of the slide, such as BREEAM, Passive House, LEED, Neighbours and Green Building Council in Australia. When we're introducing more biogenic materials, then the moisture issue becomes more of an issue than ever before. We know that a lot of these materials are hygroscopic, they can take on moisture, and if we're using larger projects, we're taking on more complex projects and more innovative timber buildings, then we've probably got higher levels of prefabrication, and it can be difficult then to keep that rain out during construction, but also difficult to seal that building in without trapping that moisture into the building as well. So we do need to be looking out for the moisture in that way. There's plenty of guidance out there in terms of helping with moisture management during construction. A must for any sort of timber or modular building, and some of the big names out there are the Structural Timber Association has their moisture management strategy document, Timber Development UK has their moisture management during construction document. There is the Mass Timber Insurance Playbook guidance, which helps with detailing and risks associated with building with mass timber. And Waugh Thistleton has released the new model building guide, which has a lot of details and things like that. So it's taking into account things that such as how materials are going to be transported to site, how they're going to be stored on site, how are they going to be protected during construction, are they going to use tapes, membranes, seals to help protect that? And then how is that moisture going to be monitored from there onwards once the building becomes watertight? Are you going to monitor any of that trapped moisture and any operational phase moisture as well? There are some statistics on water ingress and moisture in buildings. Some of the published public stats there on the left-hand side. So 10% of total construction costs, that is not just what moisture, are wasted on defects. But of that 10%, 69% of those defect claims are related to moisture penetration through the building envelope. So that's quite a large amount of those costs are related to moisture penetration. 3.3% of construction cost is wasted on water ingress. That is 3.3% of the total construction budget, which is a huge number. We talked to quite a large main contractor recently, and they said their figure was actually 2%, to which we said was quite good, but they still didn't think so. 2% of their total construction budget is still a large amount of cost. And then 2% of construction cost is spent on the roof, but that does make up 70% of all the litigation in construction. Now at Tector, we take a lot of data points through the year. We've got thousands of sensors taking data 6 times a day per sensor, so we've got a lot of data. So we've created some of our own stats as well. We're finding that on our projects, we're finding over 2 leaks on average per project. Of our 10 biggest projects, which total roughly 40,000 square meters when these stats were made, we've been finding 78 damages, which is a damage or a leak, 1 leak per 391 square meters. And of those leaks, 1 out of 10 of them didn't have any ingress before handover. So they were signed off and handed over as leak-free, and then 1 out of 10 then leaked post handover. So it just gives you a little bit of an insight into the problem. And I'm going to have a look into some of those risk areas, some of the high risk areas in construction, where we're likely to find a sort of pinpoint where the risk areas might be and the areas that we might need to concentrate on in monitoring. So what we see on site is, as a result of water ingress, is damage really to the structural integrity of the building components. That damage to structure is obviously the priority in terms of keeping a building safe. So that's what we're trying to monitor and try to prevent any damages occurring. We're seeing a lot more complex projects. We're adding a lot more complex details and systems and materials, and we're increasing the risk of leaks. The little image in the top right corner there is an image I took on an inspection years ago. This is a row of terraced houses. They're townhouses. It's something we've been building in residential construction for decades, so it should be quite a straightforward situation. Unfortunately not. There were lots of little small details, this party wall detail with capping pieces and lap membranes. We've got this parapet wall with a capping piece where the junctions between the adjacent capping pieces weren't sealed. We've got this dormer window on a mansard roof. We've got this little flat roof area that really isn't doing an awful lot. It's not like it's a balcony or a terrace area. And there were so many junctions in membranes and details that were failing that the water was getting into the building. And this was a timber frame building as well. So the bottom left-hand corner there, that image is showing some of the moisture damage in the parapet walls there. Not only had that moisture got in through and started damaging the parapet walls and some of the upper structure of the building, but it was getting down into the cavity as well, where the cavity trays weren't installed properly, and that moisture is then tracking down all the way down to the sole plates, which is essentially you're propping up your building, your lowest structural timber component. So the knock-on effects of that can be quite huge. And on top of that, if we've got high levels of moisture in the building fabric coming into the building, or even water ingress, escape of water, should I say, from wet rooms and things like that, we can get the development of mold growth on the internal surface linings as well, so which can be hazardous to health. So the biggest, probably highest risk area and the highest area of water ingress claims are in roof sections, and particularly flat roofs. And when we talk about flat roofs, we're also talking about terraces and balconies that act, if you like a flat roof, like a warm flat roof situation. Moisture penetrates beneath the waterproofing membrane and tracks through the insulation, and then it accumulates on the vapor control layer. That can then find its way, looks for breaches. It will track across the roof and look for breaches, and it will track into the structure. And if that percolates then into the structural slab panels, then there's an issue of degradation of the structural roof slabs. Obviously, at that point, that moisture is sandwiched between materials, so it's sandwiched between a solid structure, a membrane, the insulation pieces as well, and there's no then pathway for drying. There's not any ventilation in there. The water can't track away that easily because it's trapped. So those leaks can go on unnoticed for a very long time. They can get absorbed. If we're looking at decayed timber flat roof, for instance, that could get absorbed into the roof. You might end up, hopefully not, but the image on the right there, an ongoing leak that hasn't been detected can result in significant decay on the top surface. It can corrode steel, and it can structurally compromise concrete and also the reinforcement bar in the concrete as well. But this can go on with no visible evidence of leak until it's too late. So if you take the flat roof image on the left, it looks like a perfectly decent flat roof, and you don't know what's going on underneath that, unfortunately, until it's too late. It can also reduce the thermal insulation capacity, and fixing the leaks, or finding the leaks and fixing them, might improve the future integrity of the building, but it might not necessarily avoid all the damages as well. There's lots of different types of penetrations as well into the waterproofing membrane of the flat roof and in the entire flat roof system. In fact, you might look at the left image there and think that that is some good detailing around a penetration of those ventilation ducting points. The right two images show a man-safe anchor that had been sealed in, ready for insulation to go round, and on the middle image you might think that looks quite well sealed. On the bottom right corner of that man-safe anchor, you can see a little gap there. When I was on the roof of this structure, I managed to put my little finger into that gap, flag that to the site manager that I think needs a better seal. We have got dozens and dozens, if not hundreds, of penetrations going into these flat roofs. So the chances are that there are going to be some issues surrounding some of those seals are probably quite high. And aside from penetrations, you also have other activity going on during the construction phase on a flat roof, which might damage the roof as well. In this particular situation, this was a result of a pallet being stored on the roof. Heavy materials on the pallet being moved around the corner of the base of the pallet, cut through the waterproofing membrane. And luckily, this roof was being monitored, so they were able to pick up the leak quite quickly, localize it, and then patch repair it, as you can see on the right. A good question to ask, I always think, is we've been building flat roofs for decades. Why haven't we resolved these issues? Why do flat roofs still leak? I think is a good question. I think in a previous world with a flat roof, if it leaks, we'd just add another layer of bitumen or roof felt over the top of it. We might carry out patch repairs. They might not last as long as the main roof, but they might repair the issue for a few years as a temporary fix. You might use buckets. I've been in plenty of shops in my time when it's been raining where there's buckets out on the shop floor catching water leaks in the roof. It's funny to mention, but it is true. And sometimes budget restraints and wishful thinking might just come into it as well. But in today's world, we're sort of shifting away from those traditional methods. We're shifting away from bituminous materials. That could be a result of a push for more sustainable products and more sustainable membranes. It could be the difficulties in obtaining hot work permits now on top of roofs. But in addition to that, we're adding to the amount of plant in terms of things like solar and heating pump systems, heat recovery systems, lots of building plant going into this modern technology and sustainable technology. The flat roofs are an ideal place for storage for all of that. Add into that all the green roofs, the blue roofs, the water attenuation systems are actually encouraging water to stay on top of our flat roofs. So in the past, a roof has always been, in my opinion, to shelter the building and to push water off it. But now we're encouraging that water to stay on the roof to accommodate green roof systems and attenuation systems. And all of these systems that we're adding onto our roof is resulting in a more requirement for things like access and constant activity on the roof for maintenance. So the access requires those man-safe anchors that I just showed, access walkways, balustrades, and those balustrades have stanchions and those big stanchion bases. Each one of those adds another penetration over and over. And if we're using more and more of these single ply membranes on our flat roofs, then we're reliant on a single seal around any of those penetrations. Another risk area would be something like a parapet wall. So I've included some images here of parapet wall during construction, one that's had some issues post-construction. And this detail in the middle there, hopefully you can see, but that particular detail was taken from an old CLT handbook with a CLT roof deck and CLT external structural wall panel. Now, in that particular junction, we've got lots of things going on. So we've got a junction between a roof panel and a wall panel. They're both structural panels and they're both hygroscopic materials. They're both timber. Directly above that, we've got a parapet wall. We've got a box gutter. So we're encouraging all the water into that junction via the box gutter detail. We've got the parapet wall. We've got lots of membranes and lapping details of membranes to get right. We've got capping pieces over the top of the parapet wall. Then we've got a cavity and a cavity tray as well that we're hoping has been installed properly. So there's lots of little details and risk areas in that small section. And that's why we can sometimes see parapet walls and things like that go wrong. On the left image there, you just see a little outlet as well. So that box gutter flows the water through that and then out through the outlet. So the water goes through the parapet wall as well, which requires additional seals too. Facades then become a risk. We have different types of risks on facades. We've got rainwater outlets. So if we look at that outlet going through the parapet wall, on the other side of that, we'll have a gutter hopper. Now, if that hopper gets overwhelmed by high levels of water, if it gets blocked, if it's been specified wrongly and it can't accommodate the amount of water, it can overflow and it can push water down the facade of the wall into the cavities, cause subsequent leaks. We have things like the balcony details that you see in the middle image. So any structures being connected into the facade, that creates a moisture pathway then into the facade and into the structure. So if the correct seals and membranes and things like that haven't been used appropriately or it hasn't been sealed properly, there is a moisture pathway into the facade and then can lead to subsequent damages. And then we've got the bases of walls as well. So that can be moisture tracking down a cavity. That can be a failure in cavity trays, like I said earlier. But it also can be things like building a structure at ground level or slightly below ground level even, where moisture has managed to wet the structure as a result of splashback from the external surfaces, or moisture from the ground getting in past membranes that aren't sealed properly and eating away subsequently as a result of fungal decay into that timber structure. So there's all sorts of details and recommendations that are advised in the timber industry, particularly to avoid things like that happening. But it's certainly a risk area if that's the case. And what you might find is something like this. So you have a opened up area for inspection into your wall that's been getting wet for various reasons. It's had water tracking down there. And as you see, this is two adjacent areas, is exactly the same. This is one photograph. They've opened up one section of the wall and another section that was below an area of water ingress. And you can see the significant difference in how the damage has occurred in those situations. So the water's got in, it's getting trapped in between those membranes and trapped in between those insulation layers. And the damage has occurred as a relation to that. It's got nowhere else to go. It's got no ventilation to breathe. And then finally, there are sort of many other areas as well, but just trying to highlight some of the biggest risk areas. we have got wet rooms, and now wet rooms in particularly a high risk. We talk looking at something like mass timber CLT wet rooms or modular construction. They are high risk. They can, and the water escape of water can happen in various forms. That could be leaks in linings or seals. So they could be have your tiles for your shower, for instance. It could be a seal in your silicone around your shower tray, something like that, that the water just tracks through, and unfortunately you don't see any evidence of that. It could be plumbing leaks, and that could be a result of something like a shower waste or sink waste, or water feeds into showers and toilets and things, sinks like that. Those small leaks that manifest and they go unnoticed, they can be relatively common. And I think if you were to think about your own house environment that you live in, how many times you've experienced a leak in your own property, they can be quite common. So if this does happen in some of these environments, they can go unnoticed for quite a prolonged period, and the damages can be quite devastating. I just wanted to highlight really some of the damage repairs, because when we look at damages in buildings, we're not just talking about replacing a decayed piece of timber or a decayed panel or water ingress panel. We're talking about construction delay fines. We're talking about all the access requirements needed. I talked about the Sky building earlier. I know the access for scaffolding alone is into the tens of millions. It's about the design of the repair. It's about the knock-on effects, basically, of these damage costs. I'm not going to go through every one of these bit by bit, but it's just to give an oversight that there's more to these damage repairs and the costs than just the actual repair itself. And you've got things like loss of business earnings, and if this is a school or a hospital, how do you think about alternative accommodation? How do you move a whole ward in a hospital? How do you look at moving all the equipment if you're have got a massive repair in a data center, those sorts of things. So I think it's worth considering, and considering who's responsible for all those costs as well. And I think that's the big question, and that's there's a level of responsibility through every phase of the construction period. But that is enough from me. I'm going to talk about now really how Tector can track moisture in real time, how we can translate that data to prevent all these costly damages, how to give you an early warning detection that there's a problem and a leak in the building in any form. And I'd like to welcome my colleague Thijs to the stage to showcase the Tector platform really and give you a bit of a live demo on how we do that.
Yeah, thank you so much, Ben. Well done. Hi everyone. My name is Thijs van Tilburg, and I'm one of the co-founders of Tector. And I have had a lot of interaction with our clients throughout the years, and also, been connected to the solutions and how we further develop them to sort of fit the needs of our clients. So I've taken live videos of 3 projects I would like to sort of demonstrate for you that's quite different. So I have, to begin with, to follow up on Ben's wet rooms, I have a French case with how do we sort of see standout centers and how do we then find leaks using that. The second example is a very small example of how we use sort of machine learning and knowledge-based AI to sort of spot trend changes. And finally, I'll go through a flat roof that is experiencing some leaks and sort of developing water spreading throughout in a not so nice way. So I'll start out with this example here. Sure, I'll just start from over. So this project is during the Olympics in Paris 24, there was a demand for all buildings to be made out of timber. So that meant that a lot of different sort of construction methods were tried. We came in as part of one of them in the village for the athletes, where the contractor wanted to track whether they had built in, or like whether the CLT was damaged underneath in the slabs underneath the wet rooms. So this is some. So they installed 38 sensors, as you can see, and what you can see here is that the principle of it was that they installed the sensor from underneath. They dragged the screw all the way out alongside the drain in order to see if there was something that wasn't fully tightened, or like, you know, something, there was a spillage of sorts, then we would be able to track it early on. And just scrolling down for a few pictures of the installations of different sensors. Going into the overview, what we can see here is that all the sensors were built in at the same time. They have very stable data for a long time. I've highlighted a fairly long period of a month before the Olympics started. So everything was going really well, obviously, since there was no usage of the scenarios. But when the Olympics started in end of July, early August, we had 2 leaks that occurred. So you can see the first one up here and the second one here, where you really can see those spikes. The data starts becoming different than the rest of it. So we had those 2 first leaks during the Olympics, and we actually also had one during the Paralympics a few months later. So looking into how one is looking. So the first one, you can see here how it's installed next to the drain, and just so you can filter out all the other sensors. So you can see very stable levels of around 10%, 12 maybe, and then all of a sudden it goes up. So by coincidence, there's a lot of rain those days, but that's actually not the reason. It's because the athletes started to use the showers. So it's a pretty classic example of, you know, if you have a bundle of sensors and something all of a sudden is behaving differently than the rest, and they should be typically having the exact same sort of use case, then that should be you should be mindful of that. So the next example I'll show you here. Yes, that's from a small project in Denmark. It's a modular building where they installed a few sensors because of the insurance company demanded them to, in some technical shafts. So I think we had more or less just 4 sensors or 6 sensors in a technical shafts. And they were just covered in these small areas where they were covered by insulation. You can see, I think I'm highlighting the photo here. So you can see the sensor is just tucked in nicely, and it should be super stable conditions. And that's also what we're seeing, is that if we scroll down and you see, I've highlighted a long period again of a month beforehand with just super stable levels of 10% moisture, 60% humidity, and nothing is changing really. And then all of a sudden, over a period of 2 weeks, the timber moisture goes up 3%. So it's nothing that would trigger any classic alarms. It's nothing to be worried about at this stage. It's basically just still in a very good place. But our internal algorithms will spot that there is a change that is made. So we will be flagging this and reviewing it manually to be sure and verify that we think it's something worth notifying the client about. So in this case, you know, it's we deemed that since it's very clear that water is being added to a very fixed environment beforehand, we decided to contact the client. Our theory was that it would be a small pipe that was just dripping slowly away, and then in 3 to 6 months, we would have a lot of mold spread and stuff like that. That was sort of the worst case scenario, and that's one of those where it's just damages that goes really, really slow. In reality, our guess was wrong. It was a water damage that had happened a few apartments away, and that sort of started affecting the whole building. So it's interesting to see how a water damage not really next to this area still sort of is picked up by these small sensitive algorithms. The last example I would like to share with you is our flat roofs. So this is school building in Copenhagen. It's actually our first flat roof. So there's nothing bio-based here. It's classic concrete slab and then membrane insulation. And our sensors are, as Ben has mentioned, built underneath the insulation. And the full purpose of it is to detect when the upper membrane is breached, because then a damage can occur. So what I've done here is we can see that at this point in time, all sensors are displaying low values. Nothing is sort of to be worried about. And then I've highlighted a period of 5 weeks, and I can play off sort of a time-lapse video to see how it develops. So after a few days, we can see that this sensor goes from low values to 100% moisture. We can see that there's been rain at the same time. And looking at where it's placed next to a ventilation shaft. So probably a manual mistake that's made, that they haven't really tightened it the best way possible. So of course, an alarm is sent out to the users that they should just go up, fix it, and in most cases that would be it. So that means that they would just spend 2 hours and then not have to care about that problem again. Unfortunately, that's not what they did. So we have a damage that we can now display and see how the water spreads in the warm roof structure. So after 2 weeks, another sensor down here is becoming really wet. So that means that it's been pouring in one area, and then it starts to overflow, and it will run the direction that the roof slope sort of dictates, and it runs down to the atrium, where most likely it's not the point of water ingress, but instead where the path of the water will be. So continuing the video, then you can see on the right side, you can see that the increasing value, it goes from the same low levels and slowly up. So this increase indicates that it's becoming more and more moist in the area. There's not a lot of water being added, but enough to be worried about. So if we think this example out, what would happen then is, at some point, enough water will have piled up in an area. So let's assume it's around this sensor, right? So then it will find the weakest spot in the lower membrane to start penetrating the concrete, and it will start dripping. So once it starts dripping, the owner or the contractor will start looking for where the sensor is, or where the leak is. So they'll be removing, you can see here that there's solar panels and green roofs all around it, and they will be needing to remove everything in order to sort of find the leak that's actually causing this, which is obviously quite problematic. So that's the worst case scenario if you don't have monitoring. In our case, of course, we do have monitoring. So second best option, if you didn't catch it immediately, would of course be to use the system and track back of saying, okay, there's a drip. We can see that the system is showing that there's moisture here, but what would actually be the cause of it? And then you would be able to track back to the first spot. Also just displaying, we also have a risk score. That is our sort of way of interpreting data for our clients. And I'll just toggle that on now. And then it will just sort of, it's from 1 to 5 or 0 to 5 of how likely it is that there is a leak in that area. So you can see that we're more or less at maximum at the original point of water ingress at 4.8. The one in the atrium is only at 0.5, so we're pretty sure that there's no ingress there. It's just, it was passing water. And then on the right side, we can see 1.2, meaning that there's definitely something going on, but we don't think it's a local leak that's happening. It's more likely to be, what it actually is, water sort of getting trapped there because of the slope in the building to the roof. So this is a very example I use quite often because it's very easy to see what would have happened with or without a system like ours. Very good. I'm guessing, Ben, maybe you would like to join me on here if there's any questions.
Yeah, brilliant. Thanks, Thijs. I do have one question for you. Which is for someone watching today who wants to introduce moisture monitoring on their next project. What's the single most important first step, in your opinion?
That's a big one.
Yeah.
Well, I guess it's about the first step is to find out what the purpose is, right? To actually have defined, is it because you feel uncomfortable with what you're building, or is it because you want to mitigate risk, or what's the defining reason for it? Because if you know that to begin with, then in the second step, you would be able to sort of make a risk assessment of the entire building, right? That means you can either talk to some external advisors or just ask Ben or I to sort of have an overview of what risks do that specific project have, because we can, with a fairly quick scan over the phone or an online meeting in 15 minutes, we'll know what will be the most likely areas for moisture damages, and in that way to give sort of a platform to take the discussion with the other stakeholders in the projects. That would be sort of how I would go about it. What do you think, Ben?
Yeah, no, I completely agree. I think it's something that we evaluate on a project by project basis. So it's having those initial chats about the projects and the systems and the details and things like that you're proposing on using, and it's that initial consultation is the first step, and we would take it from there, really. Another question's just come in, Thijs. Do you position the sensors at the same depth within the timber? And do your algorithms use different threshold values depending on environmental factors like relative humidity and temperature?
Yeah, that's why you should be talking to especially Ben, is because he'll know exactly what sort of depth, because it won't be the same depth. It actually very much depends on which area we're monitoring. Sometimes surface depth is a great place. Sometimes we want the core, and other times we just want to not have the surface, but not too deep, so it could be 10 mil in. So I think that very much depends, and we can supply sort of different insulated screws in order to measure different depths. And then on the different threshold values, that's something we go into a dialogue with the customer. So we don't want the same alarms for all construction parts. So we of course have a unique alarm set for our warm roofs, but for timber construction, it's very dependent on if we have we can place quite sensitive alarms. That would be, for example, underneath the CLT in a wet room. We know that it should be stable, same as a sort of a riser or technical shaft. Then we'll make either very low values of a threshold, or you can also create alarms that will trigger if there's a movement, a small movement. So let's say we want to trigger it if it goes up 2% in a short period of time. That's because water has been added. So yeah, we have quite a few options in order to sort of create a unique alarm system for each subgroup or like construction part.
Yeah, brilliant. And just to add on the timber and the depth and things like that, it is again depending on where we're monitoring. So we have different types of hardware. Sometimes it won't actually be connected to the timber. We've got the loose monitoring sensors that go in and they're not attached to the structure itself. If it is attached into the structure, but it's not wanted to be visible, for instance, on the internal side of the building, we would look at finding a way of either building that into the fabric or having it on the outside of the wall or the ceiling, or wherever we place it, using different sort of accessories. So like Thijs said, the insulated probes, or we can extend the probes as well for those hard to reach places if the sensor doesn't fit into those areas. But it's about, designing the system to suit the project. Well, I don't think we've got any more questions coming in, so I think we will call it there. Thank you very much, Thijs, for your demonstration at the platform, and thank you to everyone for tuning in today, and hopefully we'll see you on the next one.
Perfect. See you guys. Thank you for today.
Bye bye.